Okay, good morning, everyone. It's a great pleasure to finally be able to speak to people face to face again. It's really amazing. The last time we have been speaking like this in front of other people was more than a year ago, I guess. So I'm really, really happy. My name is Krueger. I'm originally from Germany. I'm a not so new recruit anymore, 1.5 years in the physics department and Solid-State Institute. And I work in kind of a different field from what you just heard in the talks before me. I'm working on imaging ultrafast quantum dynamics, both in space and time with extreme precision. So let me start and explain to you what I mean with ultrafast. So if you think about the Bohr model of the hydrogen atom, which is, we know it's wrong, the timescales that we associate with it, we can describe them by atomic units, atomic Hartree units. You know the atomic unit of time is 24 times 10 to the minus 18 seconds. That's the atomic unit of time. And 2 pi times this time is the Bohr orbit time. It's the time that in the wrong Bohr model the electron takes to perform its orbit. And 10 to the minus 18 seconds, this is 1 attosecond. This is the time scale that we are working in my lab. But I also want to point out that this is not just for the hydrogen atom or for atoms in general. This is for molecules, for solid-state systems. This is electron dynamics. This is the natural time scales of electrons. Then we also have the atomic length scale, which is the Bohr radius, which is 0.5 angstrom. Just to put this a bit into scale here, 1 attosecond, if you invert that, go to 10 to the power of 18 seconds, you end up with the age of the universe as we know it. So it's basically comparing 1 second to the age of the universe is comparing 1 attosecond to 1 second. So we are talking about extremely short times here. Okay, so what happens on the attosecond time scale? I would basically say it's the rearrangement of electrons in response to some external perturbation. For example, the creation of electron-hole pairs for example, we know from the solar cells, or the photoelectric effect when a laser pulse hits a metallic system, or even the dissociation of molecules. So electron rearrangement, the natural time scale is attoseconds and femtoseconds. Okay, let's talk a bit more closely about what happens on these ultra-short timescales. Let's assume we have a quantum system that sits in some state. It's just one electron. We just look at a single active electron for this point. If we excite this electron, we can put it into a quantum superposition. That's nothing really exciting. But when we assume, for example, let's assume we have a molecule that's diatomic, that has 2 different excited states, one with a S symmetry and another one with a P symmetry. This superposition, when it evolves in time, will lead to beating. The probability to find this electron at a certain point in space oscillates because it's a quantum superposition. This is a coherent evolution of this quantum system, but at later times, what happens is that because of coupling to other degrees of freedom and other dephasing mechanisms, decoherence takes place, and we end up with some final state of our quantum system. The challenge here is, if we really want to take a look at what happens in these initial times, these electron dynamics that's coherent right after the excitation, we are basically lost. We cannot just look at the final outcome. We have to perform spectroscopy in the time frame when all these effects actually take place. Indirect methods, for example, measuring line widths in spectroscopy, they can tell us something about temporal dynamics, but it doesn't allow us to look at the actual coherent dynamics that happens at the very beginning. So why is this important? Because we believe that at very short times, not just the one electron that we are talking about plays a role, but it also talks with other electrons. So we are talking about many body effects, multi-electron systems. Okay, so how do we get to these short timescales? I want to focus about a very simple system for this point. And this is simply an atomic system that's exposed to a laser pulse. And we look at photoemission, the emission of electrons from this atomic system. And I also want to introduce you to the temporal perspective of this effect. So ultrafast photoemission processes, what do we have? The first effect I want to talk about is very simple. It's simply Einstein's photoelectric effect. You have a single photon, electron absorbs that photon and gets emitted. If we look into the time domain, this red curve here, over here, is the temporal profile of this light pulse. And we know that the emission rate that follows the shape of the pulse. So basically, the shorter the pulse is, the shorter the emission duration of the electron. Now, we can now decrease the photon energy and extremely increase the intensity of our pulse. Then we come into a regime where we talk not about a single photon, but we talk about the absorption of many photons from the light field, a multi-photon photoemission regime. This is a nonlinear effect, and therefore, if you look at the emission process in time, it will be significantly shorter than the pulse duration. So here we already achieve emission durations that are shorter than the duration of the light pulse. But that's not the end of the story. There is also the tunneling regime, where the electric field of our laser pulse becomes so strong that it is very violent with the atom. It bends the potential, the Coulomb potential of our atom so strongly that a tunneling barrier is formed, and the electron can escape when the electric field, the optical field, is at its peak. And in this case, the photoemission rate in blue resolves the cycle structure of our laser field. So here, if we think about a laser field, for example, near-infrared at 800 nanometers, the optical period is 2.7 femtoseconds. That means that these blue spikes of photoemission rate are already below 1 femtosecond. This would be the attosecond regime already. Okay, but for the atomic case, that's not actually the end of the story either, because we can also take a look at what happens to the electron after it left the system. When it left the system, it's a very simple way to think about it as a classical point particle. And this classical point particle is exposed still to the laser field that led to the emission by the tunneling process. So let's assume here we have here a laser electric field. Electron gets emitted at the peak of the laser field. Then it propagates inside the laser field and is eventually, when the laser field changes sign, it's accelerated back to the original ion where it came from. And when it collides with the ion, several effects can happen. And this is a very foundational process that we call recollision. The first effect that we see is that electrons get fully elastically scattered from the ion. This effect is called rescattering, and it leads to the creation of high energy electrons because they can gain much more energy in this process. The other effect is fully inelastic, when the electron then loses all its energy and recombines into the ion. And the energy is radiated off as a photon, as a high energy photon, and this leads to the generation of attosecond light pulses. So this is what we call attosecond science, and attosecond science is based on coherent field-driven electron dynamics. We have strong laser fields that we shape and that interact with electrons here in the gas phase and create light pulses, and the interaction times are in the attosecond regime. So the problem in attosecond science that we are facing, that we are mostly talking here about atomic gases. atomic gases are very simple systems, and we usually also talk only about a single active electron. We set out some time ago to study the same kind of effects in solid systems at solid surfaces, at the surface of solids. And in this case, you find a very similar picture to what I just showed you with the atomic systems. The emission of electrons from a metallic surface follows the same principles, essentially. The only difference is that in the tunneling regime, because you break the symmetry between the metal and the vacuum, you can only emit electrons in the forward direction. So only as the certain field polarity leads to the emission of electrons. So we get an electron burst every cycle once. To actually observe this effect has proven to be highly challenging, but we have been able to observe this some time ago in a very special system where you can also already see that we now go not just to very short times, but also to very small spatial dimensions. This object here is a metallic nanotip. These metallic needle tips end in a very sharp apex structure, and electrons get emitted when you focus a strong laser pulse on the apex of these nanotips. And we set out with the question, can we observe the tunneling photoemission process, where you actually have this attosecond time resolution, you have these electron bursts, and can you observe this rescattering effect where the electron comes back and elastically scatters. And the experiment itself was pretty simple. You focus such a very short laser pulse onto the nanotip, you observe its electron spectrum. Now the question is, why do actually all the electrons come just from the sharp end of the tip? That's not very obvious, because you illuminate a pretty large portion of the tip in this case. And the answer is that the tip actually acts like here the TV tower in Berlin. So you can see the lightning strikes here, and this is the lightning rod effect. And the same thing happens to the optical field in our nanotip. So the nanotip, this is here a Maxwell equation simulation of our nanotip. Here at the sharp end of the nanotip, you get a very strongly enhanced optical field. And if your emission process is nonlinear, it means that only here at the sharp end of the tip, you get the electron emission. So here you have this enhancement effect, this plasmonic enhancement effect. The nanotip acts as an optical antenna. So what we found in the experiment was very influenced by an invention that has been awarded with the Nobel Prize in 2005. It's the frequency comp and the K-envelope phase. And here I'm talking about our short laser pulses. If you look at a laser pulse that is, from my perspective at least, is very long, it's sufficient to describe the electric field by an envelope function and by a carrier wave. But if you go to very, very short laser pulses that consist only of a few optical cycles, for example, these 4 femtosecond laser pulses, you will see you need another quantity, this phase shift here, to describe these laser pulses. You can see for different phases parameters here, you get very different waveforms. You don't change anything else. You don't change the intensity. You don't change the pulse duration. You only change the evolution of the optical field within the envelope. You modify its waveform. So we performed an experiment with the nanotip, and we measured electron spectra. The result you can see here, this is the kinetic energy of the electrons. This is the count rate of the electrons. So exposing the nanotip to fields on the order of volts per angstrom optical fields led to tunneling emission, so we were able to show this. And also we were able to show for the first time the effect that electrons were scattering off and gaining high energy. In this part of the spectrum here, you can see these electrons that perform this recollision mechanism. This was a big surprise back then. But this is not the end of the story, because we know that both the emission process, the tunneling emission, and the recollision process when the electron propagates in the laser field, they depend very strongly on the actual shape of our laser pulse, of the waveform of our laser pulse. So what we did is we changed the phase of these laser pulses, this very short laser pulse, and looked at how this emission process would respond to this change. This is what you can see here. This is the phase as we change it. And here, this is this part of the spectrum. And if you look very closely, you see that for some instances, you see a very strong peak structure. And in other instances, you don't see, you basically just see noise. So how do we understand this? If we look at the two cases here, we have a peak structure, very strong peak structure, and here a very noisy structure. We can understand this as a double-slit experiment in the time domain. So if we give the electron the possibility to leave the metallic surface twice during the laser pulse, we give the electron the possibility to perform a temporal double-slit experiment. This then leads to the peak structure. But when I change the waveform of my laser pulse by changing the phase, only one contribution takes place. We have a single slit in time. So here we have actually a quantum experiment that we know from the spatial domain, but here now in the time domain. And by looking at the spectral interference that we see here, we can also estimate the temporal characteristics here. The spacing of these peaks is the photon energy, actually. And this means that the slits are spaced by 2.7 femtoseconds. So we get one emission per optical cycle. And the duration of those slits emission can be estimated from the width of this energy spectrum here. And that's approximately 450 attoseconds. So here we really have achieved, using laser pulses, a control of electron emission on the attosecond time scale. And because we also use nanotips and the electrons come from a very tiny area, we really were able to achieve control of electrons on the attosecond time scale on the nanometer length scale. So this has led to a small field of research that is developing now over the world. But we want to now go ahead and actually say something about ultrafast quantum dynamics. So let me come now to our plan. So we are working at the moment very hard to get our lab running. The lab is not yet ready, but thanks to Ido Kaminer, we already perform first experiment at the moment in his lab, in a temporary lab. So let me explain a bit about our plans. So we want to see electronic wave functions in space and time. And there has been a standard method of imaging of electronic wave functions around for quite some time. This is a method that's called scanning tunneling microscopy, STM, where you also have, you can already imagine, you have here a nanotip, and this nanotip scans over a sample, and you apply a voltage, and you get a tunneling current between the tip and the sample, and you can gain, when you measure the tunneling current, you can gain a very nice image of the topography of any kind of conductive sample. For example, here you can atomic resolution in HOPG, which is nothing else than graphite. This is not the end of the story. It's not topography only. It's also actually electronic wave functions. You can put a molecule on a surface, and you can actually resolve its orbital electronic structure. You can, for example, this is here pentacene. You can see that you can observe the highest occupied molecular orbital, or also you can actually image the lowest unoccupied molecular orbital, because by tuning the voltage in the STM, you can access different electronic states. So this is an amazing method to measure electronic density, electronic wave functions in space. So now we want to go ahead and combine this with what we have learned from the nanotip photoemission that we can control on the attosecond timescale. So we are currently working very hard on combining the ultrafast with the angstrom length scales. So we are at the moment constructing a scanning tunneling microscope. We will use these laser pulses that are very short, that are phase controlled, to control the current between the tip and the sample. We replace the static voltage in STM using a short laser pulse. And by this, we hope to be able to control, to limit the transfer of the electron from tip to sample to times less than 1 femtosecond, and also to control the direction of the current, because by changing the polarity of our waveform, we can also control the direction of the current. So this will enable us to excite systems and to read out systems on a very, very fast time scale. So, we also working at the moment on an experiment where we expose also molecules, just as I showed you, to laser pulses, and we hope to observe here an effect which is called charge migration. In these molecules, if you create a hole in a molecule, you remove an electron, and usually the hole lives also in a superposition of different empty orbitals of the system. And it turns out that there are predictions that this hole density, the density of this hole state, also migrates throughout a molecule on a very, very fast time scale. And we hope to actually see that experimentally. That's very interesting because here actually many body effects play an important role. Because you're not just talking about a single hole, you actually talk about multiple hole states. So configuration interaction plays an important role here. And also we have another project which is not so much related to the attosecond regime, where we want to image charge dynamics in samples by using again a nanotip as an electron source, but not just as a source of electrons itself, but of electron pulses. So we want to expose a sample to electron pulses and record electron hologram of the sample on a screen. It's inline holography. And then we want to excite that sample and with another laser pulse, we want to see how it evolves in space and time as well. This is a bit different approach. Here we aim at the observation of charge dynamics, for example, in nanowires or measuring plasmonic fields. Okay, so this brings me to the end of my talk. So we are hunting for fundamental physics at these very short time scales in systems of small size, in molecules, nanowires where you have limited dimensionalities. And we want to see if we find coherent effects on these short time scales. I want to, in the end, thank my team. So we have actually grown quite a bit in our group. And also our collaborators, Jonathan Beckenstein, Ido Kaminer, and Oren Cohen, and also all the people and foundations that support us. And I thank you for your attention.
Go ahead.
So this short pulses of the STF tip, what energy scale would that give you?
So because we have to regard here Heisenberg's time energy uncertainty, the energy resolution that we will achieve here will not be very small. So we're not talking about milli-electron volts, but we're talking more about the electron volt level.
So you'll be able to probe like the von Howard gap or many body gaps in around the, let's say, 8 electron volt or 6 electron volt.
Exactly, yes. So these kind of phenomena are within the reach of our method. But milli-electron volts, like typical superconductors or so, this is something that's totally out of range. Yeah.
Well, that you do in DC. I mean, you
Exactly.
have
Yeah.
a different problem.
Mhm.
Are you not going to damage the samples that you're going to choose very high energy electrons to sample?
Sorry, I did not. Can you speak up, Nathaniel?
Damage the samples that you're trying to probe.
So this is actually a point of concern, but we have found out previously that if you choose these pulses to be very, very short, the interaction will not actually damage the sample. So if you are in field strengths of volts per angstrom, which we achieve with our nanotip, it has turned out that you actually don't damage the sample on a long-term basis. It's simply a factor of the pulse duration versus the average power you illuminate the sample with.
You're speaking about the tip.
Yes.
I'm thinking about the sample that you're trying to probe.
Also the sample, actually. So molecules, also molecules have been exposed to strong electric fields in so-called terahertz STM. Terahertz STM you use very strong terahertz transients, and also here the molecules have remained stable. So it is a bit of a point of concern, but we have a very good chance at that from what we know. Mm-hmm.
So in the double-slit temporal experiment,
Yes.
I guess that to be able to see interference, you really have to make sure you don't have which-way information, right? You have to be distinguishable. But in your experiment, what sets this? I mean, how do I know that the electrons are really indistinguishable, the ones that leave at different times and are not somehow labeled by some information in the tip?
In the experiment I showed you, the electrons are indistinguishable because you actually see the interference pretty strongly. The thing is that, of course, in our metallic tip we have many electrons that are exposed to the same light field, they respond to the same light field, but they sit approximately the same energy. So even the incoherent superposition of all those electrons, what they do in the laser within the laser pulse, they behave very, very similarly. So we still see this interference pattern very, very clearly. The interference of each electron with itself, although you actually address many electrons. They sit at the same energy, and the superposition of those still give you this kind of very strong interference pattern.
But what affects the visibility of this interference in your what parameter?
We know from experiments that look at coherence of electron field emitters, that what is the limit here is the electron-electron scattering, the mean free path, and that is people say that the length scale that you have to think about at a metallic surface is about 100 nanometers, which is really, really large number. This would be the main decoherence effect in this case.
How do you know that in the experiment, every electron interferes only with itself and not with others? How do you know experimentally? Not in the equations, I know to write them. In the experiment, how do you distinguish between these?
If an electron interferes with another electron, they sit at they start out usually from different energies. So let's say they are not don't talk about degenerate case. In this case, the relative phase depends on this energy difference very strongly, and this will lead to a strong modification of this interference pattern.
But they can start from the same energy, only slightly different locations.
Yeah. So.
Start off, okay?
Mm-hmm, mm-hmm.
And the same spin, and in principle, if you put the theory aside that assumes it's
Okay.
possible, it's not proven in any experiment to the best of my knowledge.
That's very interesting.
How would you know?
I have not thought about this question yet.
So think about it. It's a fundamental question, and if you resolve it, it will be very important. I mean, people assume it. When you teach quantum mechanics, that's what we assume, but it's not necessarily true.
Very interesting. Thanks, Morty.
Anyone else? No. Okay, so let's thank the speakers.